Good morning, Year 13. Today we're going to start off the astrophysics topic by looking at converging lenses which are needed to make telescopes. So there's some evidence to suggest that the earliest lenses may have been over 3,000 years ago, and these were made in order to start fires by focusing sunlight, just in the way you could use a magnifying glass to do so right now. It wasn't until the 17th century that lenses were being used to make telescopes. The process of refraction is something that you would have covered last year, so I'm assuming that you remember a fair bit of this. But when light passes from air into the lens, it slows down. So as you can see, this ray of light enters the lens, and because it slows down, it moves towards the normal. As long as it's not coming along the normal itself. As the light leaves the lens and enters air, like we have over here, it will bend away from the normal as it speeds up again. Convex lenses, like this one, we've got a side view at the moment, is designed to have the correct curvature needed to bring parallel light to a focal point. So this diagram here shows that we've got rays of light entering parallel to something called the principal axis. Such rays of light are going to be refracted towards the principal focus, so a focal point here which is known as the principal focus. The distance between the lens axis, which would be this line here, and the principal focus is called the focal length. This diagram here shows us quite an interesting phenomenon. So you'll notice that as the lens gets thinner and thinner and thinner, the ray of light passing through it at the centre becomes less and less deviated. So if we have lenses below a certain thickness, we know that the ray of light that passes through the centre of the lens isn't going to change direction. So this is going to be quite important when we start to draw ray diagrams in a moment. In this diagram we have three rays of light that are entering the lens not parallel to the principal axis. So because they're not entering parallel to the principal axis, they're not going to get refracted to the principal focus. They're all going to get refracted towards a different point in the focal plane. If we go back and look at the centre of our lens, because this is quite a thin lens, as we mentioned earlier, this ray is not going to be deflected. So that will tell us where on the focal plane the rest of the rays of light will converge. Okay, so what we're going to do next is use what we've just seen to try and draw a ray diagram for an object placed different distances away from a converging lens. So the first thing we're going to start off by doing is drawing a horizontal line using a ruler across the top of our page, and then around halfway along that I'm going to draw a line at 90 degrees to this. So the first line we drew, this is going to be our principal axis, and the vertical line we drew intersecting it is going to be our lens axis. So this would be the centre of our converging lens. And to show that we're drawing a converging lens, I don't need to draw the whole side view of the lens. All I need to do is draw something that looks a little bit like that in the middle, and that tells us that it's a convex converging lens. I'm also going to mark up the focal length of my lens. I'm going to choose 4 centimeters as a focal length, just because that means it fits on my bit of paper quite nicely. So I place my ruler here, and 4 centimeters away from the centre of the lens, that's my principal focus. And we'll label that with a capital F. And on the other side of the lens, because it's symmetrical, we'll have another principal focus that is length, also labelled up as F. So this focal length here will be 4 centimeters. I'm going to draw another mark 4 centimeters past our first F here, and on the opposing side. And this I'm going to label 2F. because it's double the focal length. So we've now got our axes set up, we've got our distances marked up, we now need to place our object. So all we're going to do is draw an upright arrow. I'm going to start by drawing mine at 2F, and I'd like it to be 1.5 centimeters, 15 millimeters high. So that is the object. You can draw something more complicated, but an arrow is fine. I'd always stick to drawing an arrow. So we're going to draw 2 rays of light. Both of our rays of light are going to originate, they're going to start at the top of our object. In fact, I might just label this object now before we go any further. And my first ray of light is going to go as best I can parallel to the principal axis until it hits the lens axis. So I think that's not too bad. And there's our first ray of light, and because this ray of light has entered the lens parallel to the principal axis, just as we mentioned earlier, it's going to travel through this principal focus at F. So I'm going to continue this ray of light. It's deviated because it's passed through a lens, and it's going through at this point here, and I'll put another arrow on to show that it's travelling in that direction. So that's our first ray of light complete. Our second ray of light is also going to originate from this point, just as we mentioned earlier, and it's going to travel through the centre of the lens. That looks okay. I'll draw my ray of light. And it looks like that. So as we mentioned previously, it's going through the centre of our lens, so it's not going to be deflected, it's going to carry on moving in a straight line. And you'll notice at the right hand side of our diagram, our rays of light converge, and this is where we put at the top of our image. So the top of our image will be at the point where they converge, and you draw your image vertically like this until it reaches the principal axis, and let's label that image. And we can look at the image that we've drawn, and we can notice a few properties about it. So as you can see, it is inverted. It's the same size as the object, and it is the opposite side of the lens to the object. And this is the key thing I'm going to look at. I'm interested in the fact that it's inverted. If it's inverted, we know that the image that's produced is what's called a real image. If we were to draw a ray diagram and get an upright image, that would be what's called a virtual image. So real images can be projected onto screens. Virtual images cannot. Okay, so we're going to have a look at a similar diagram, but this time we're going to place our object in a different position and see what that does to the image that we're going to produce. So previously we placed it at 2F. This time I'm going to place it between F and the lens. So the distance between the lens and the object is going to be shorter than its focal length. I'm going to use the same object, the same size, so it's just going to be a vertical arrow, 15 millimeters in height, and I'll place it here. So just as before, we're going to draw 2 rays of light, and they're both going to originate from the top of the object. The first one is going to travel parallel to our principal axis, and then when it hits the lens axis, it's going to be deviated towards our principal focus. Again, it's a converging lens, so I've just drawn a tiny little convex lens in the centre here where the lens axis and the principal axis meet. That tells us that it's a converging lens. So here's my first line, and as mentioned, we'll draw it going through the principal focus. Okay, and we'll put little arrows to show that that's the direction that the ray of light is travelling in. And then our next one is still going to originate at the top, just like our previous one did, and this time it's going to pass through the centre and it's not going to be deviated. Okay, so we can see a problem straight away. These two rays of light are moving away from each other, they're diverging, so they're never going to meet. The way we get past this is by extrapolating, drawing construction lines to show where they would have met if they had been travelling in the opposite direction. So I'm going to use dotted lines to continue, like this one, and same over here. And where our construction lines converge, this is where we're going to draw our object. I beg your pardon, this is where we're going to draw our image. So you'll notice this time that our image is upright. And when we look at it in comparison with the object, it's much larger. So it is magnified and it's on the same side of the lens as the object. If I go to my defining characteristic here, it's upright. If it's upright, that means it's not inverted. That means it's got to be a virtual image, so this cannot be projected. Cannot be projected. Okay, so let's try and collate what we've seen so far. The first object that we drew was at 2f. We spotted that was inverted. It was actually the same size, so it's neither magnified nor diminished. It was opposite the object, and because it was inverted, we know that it was a real image. The next one we did was between f and the lens axis itself. Well, this was upright, it was magnified, it was the same size as the object, and because it was upright, we know that it was a virtual image, not a real image. So what you need to do for the rest of the session is to draw ray diagrams for yourself. So have a go at these two, and they'll just be identical to the ones that I drew, hopefully, if we're doing it right. Then we need to draw them between f and 2f. So if I go up to my previous diagram, you would draw your image somewhere in between f and 2f, and again I'd recommend a 1.5 centimetre high arrow as your object. I'd also like to see at f, so place it here, and then finally beyond 2f, so that means you're going to place it out over here somewhere. So in total you should have drawn 1, 2, 3, 4, 5 array diagrams. 2 will be the same as mine and 3 that we haven't seen before. You might notice something interesting about this one. I'll wait to see how you get on. Thank you.